This is no comet. At least, not any comet we've seen before. And it certainly didn't originate here. Just months ago, 3I/Atlas was nothing more than a greenish smudge lurking at the edge of our solar system. Today, it's hurtling toward the sun at nearly 70 kilometers per second, cloaked in a massive coma that dwarfs entire planets. Even more unsettling, it's transformed from green to a foreboding deep red. But here's the part that has astronomers baffled. The color shifts make no chemical sense whatsoever. The glow oscillates between red and green without warning or pattern, while the core remains completely obscured. Its size unknown, potentially anywhere from the dimensions of a city block to those of a mountain. If 3I/Atlas has truly shifted to a reddish hue, what does this transformation tell us about its real identity? And what exactly are we witnessing as this alien wanderer barrels toward Mars and the sun at this very moment? 3I/Atlas is tearing through the inner solar system at nearly 68 kilometers per second. To put that in perspective, that's over 240,000 kilometers every single hour. It's fast enough to traverse the distance from Earth to the Moon in less than 90 minutes. Compare this to Mercury, the fastest planet in our solar system. Atlas is moving at roughly twice Mercury's orbital speed and more than 10 times the approach velocity of most long-period comets as they near the Sun. This isn't a leisurely drift through space. It's a kinetic assault, a visitor from beyond the Sun's gravitational reach, plunging inward with energy that overwhelms anything in the planetary neighborhood. The trajectory of 3I/Atlas tells its own story. It's hyperbolic. The path is not gravitationally bound to our Sun. This is a one-time visitor, just passing through. The inbound speed clocked at over 60 kilometers per second before reaching perihelion. Categorically rules out any possibility that this object originated from the Kuiper Belt or Oort cloud. Only a genuine interstellar traveler arrives with this much raw momentum, untouched by the slow, looping orbits characteristic of native comets. Velocity on this scale means the forces at work are immense. As Atlas barrels inward, solar radiation and the solar wind slam into its coma, stripping away material and charging particles at a rate rarely witnessed. The object's kinetic energy, driven by that staggering 68 kilometers per second velocity, is sufficient to vaporize surface ices and blast dust outward in a violent shock of activity. Every single second, it covers a distance equal to the width of a small country. These are not the numbers we typically encounter in conventional comet science. This is something fundamentally different, a body moving too fast, too straight, and too powerfully to fit the profile of anything born within our solar system. Enveloping 3I/Atlas is a dusty shroud, so vast it nearly defies comprehension. Even the most powerful telescopes on Earth, Hubble Gemini, the Nordic Optical Telescope, can only capture a faint glowing envelope, with a true outer edge lost against the background darkness of space. The coma, composed of dust and gas swept outward by solar radiation, expands for thousands of kilometers, completely overwhelming any trace of the object's solid core. At best, high-resolution imaging places a nucleus at less than 5.6 kilometers across. However, some estimates, based on the amount of sunlight the coma reflects, range from as small as a few hundred meters to as large as 50 kilometers. That of variation spanning more than 2 orders of magnitude. The only certainty is that the nucleus is utterly dwarfed by its own outflow, hidden inside a haze that could be many times wider than the planet Mars itself. This kind of scale isn't merely spectacular. It's a fundamental measurement problem. Every attempt to determine the core's actual size crashes into the same obstacle. The coma outshines and outnumbers the nucleus by orders of magnitude, scattering light and concealing the object's true shape. Even with our best data, astronomers are left with a range of possibilities rather than a definitive answer. If the core lies at the smaller end of estimates, it would rank among the tiniest interstellar objects ever detected. If it's larger, it could rival the biggest known cometary nuclei in existence. Until a spacecraft performs a close flyby or a perfectly timed stellar occultation reveals the interior, the heart of 3I/Atlas remains an enigma, fueling ongoing debate over what we're actually witnessing and what we should even call it. Inside the offices of the International Astronomical Union, the official designation for 3I/Atlas has become a point of contention. The last time planetary definitions underwent revision, the fallout from Pluto's demotion lingered for years. This time, with a rare interstellar visitor at the center of the controversy, the stakes are even higher. Social media amplifies every rumor and theory. Science communicators field endless questions from classrooms and newsrooms alike. Should we call it a comet, a planetary fragment, or something entirely unprecedented? Without conclusive evidence, a premature reclassification could undermine public trust, blurring the crucial distinction between informed speculation and established fact. For now, the official guidance remains steady: wait for the data, keep the narrative consistent, and prepare for the possibility that the next observation could overturn everything we think we know. The first polarimetric images of 3I/Atlas arrived in late July, and within hours, the data triggered a storm of scientific speculation. Dr. Tony Santanaros and his colleagues at the Instituto de Astrofísica de Canarias had just finished calibrating a series of exposures from the Nordic Optical Telescope. They expected the usual diffuse haze, random, featureless, the kind of cosmic fog typical of comets. Instead, the data plotted as a clean, steep curve with negative branch that dropped lower and sharper than anything in the existing catalog. The degree of linear polarization, measured as the angle between incoming sunlight and scattered light from dust grains, reached -2.8% at just over 6 degrees phase angle. This is a value more commonly observed in distant centaurs than in comets. The inversion point, where polarization shifts from negative to positive, landed precisely at 17 degrees. Again, a match for objects in the outer reaches of the solar system, not the inner zones where comets typically reside. Santanaros remembers the moment vividly. We barely had enough nights to capture the coma's signature before it evolved. Each new image changed the story. But as the team pushed their data reduction pipeline further, searching for rumored concentric bands, the maps remained stubbornly uniform. There was no sign of rings, no double-layered shell, just a homogeneous field. Cross-checks with the FIRS 2 instrument on the Very Large Telescope in Chile and the Rosen Observatory in Bulgaria confirmed the result. Any variation in polarization across the coma was below 0.2%, well within instrumental noise. Synthetic data runs designed to test for hidden features produced the same outcome. The coma's structure was smooth. The polarization curve was dramatic, but the spatial maps revealed no secrets. The absence of ordered rings didn't diminish the shock of the discovery. The phase angle behavior alone set Atlas distinctly apart. The negative branch, so deep and narrow, pointed to dust grains larger and darker than those found in typical comets, possibly aggregates interlaced with organic compounds, and ice is formed in the coldest corners of interstellar space. Models built for solar system comets failed to reproduce the curve unless they borrowed parameters from small trans-Neptunian objects like Pholus. That left the team with a profound puzzle. An object that resembles a centaur, moves like an interstellar visitor, and scatters light in a way no comet has before. The evidence was clear, even if the underlying physics remained mysterious. For Santanaros and his peers, the surprise wasn't in the absence of rings, but in the unmistakable signal that 3I/Atlas refuses to conform to any standard classification. Dust from interstellar objects is often imagined as a random mixture of tiny grains, drifting and shaped by the push and pull of sunlight and solar wind. With 3I/Atlas, the evidence points to something far less ordinary. The polarization curve, marked by a pronounced negative branch and a sharp inversion at 17 degrees, signals the presence of large, irregular aggregates. These aren't the compact, bright grains familiar from most comets. Instead, they're loose, porous clusters woven from organics and ice, their structure more resembling tangled webs and polished stones. Such aggregates scatter light in ways rarely observed in the inner solar system, hinting at origins in colder, darker environments. The coma's polarization map adds another layer to the mystery. If plasma effects or engineered structures were shaping the dust, distinct rings or bands would appear as clear, organized patterns in the data. Instead, the coma remained smooth, its polarization varying by less than 0.2% across all observed fields. Independent measurements from FIRS 2, Alfosk, and Rosen confirm this uniformity. There are no signs of jets, shock fronts, or plasma waves at work. The data consistently point to a population of large, dark aggregates closely resembling dust observed on Centaur Folis, and some small trans-Neptunian objects. This resemblance isn't merely superficial. The deep negative polarization branch and red spectral slope both indicate dust that has endured millions of years in the outermost reaches of a planetary system, altered by cosmic rays and coated in complex organics known as tholins. For 3I/Atlas, the coma becomes a record of another star's debris disk, with each aggregate grain preserving clues to its own formation and chemical evolution. The absence of order rings narrows the field of explanations. Rather than plasma-driven or artificial origins, the evidence favors natural but rare dust aggregation. Materials shaped by interstellar weathering, assembled far from any sun, now passing through our sky for the first time. A single photograph snapped in the pre-dawn hours of September 7 from the Namibian highlands electrified the astronomy world. The object at the center glowed a vivid, almost neon green, startlingly bright against the dark sky. The photographer, known for capturing rare cometary apparitions, had set up with a complete suite of filters, expecting the familiar red hue that had dominated every scientific report to date. Instead, the camera's sensor recorded a color that simply didn't belong: green, as if the interstellar traveler had swapped its ancient, weathered cloak for something alive and volatile. Within hours, the image circulated through astronomy networks and landed in the inboxes of professional observers. The confusion was immediate. All previous spectra, from the Nordic Optical Telescope to JWST's near-infrared scans, had shown a steep red slope, 18% per 1,000 angstroms, redder than most comets, a perfect match for Centaur Folis and the darkest trans-Neptunian objects. This redness was no accident. It was a signature of grains battered by cosmic rays, coated in organic tholins, and shaped in the coldest reaches between stars. Yet here, in a single night, the object shone green as if its chemistry had shifted in real time. The usual culprit for cometary green is the C2 molecule, which fluoresces when broken apart by sunlight. But days before, high-resolution spectra from Chile and La Palma had shown almost no C2 emission, an absence that seemed to rule out the standard explanation. Chemists suggested alternative candidates. Perhaps trace CN or even CO could be responsible, but neither had been detected in significant amounts. Some pointed to the possibility of ultrafine, icy grain scattering light through Rayleigh effects as the coma's dust population evolved. Others wondered if the filter response or sense of bias had amplified a fleeting wavelength-specific burst. The debate spilled into preprint servers and social media, with every new theory chased down by teams eager to explain the color mismatch. The photographer's raw files, released for open analysis, confirmed the event wasn't a processing artifact. Multiple amateur astronomers across southern Africa reported a similar green tinge, though none as striking as the original image. Within 48 hours, professional observatories had retargeted the object, hoping to catch a repeat performance. None did. The green vanished as quickly as it appeared, leaving behind a trail of unanswered questions. Was this a transient chemical outburst, a rare scattering event, or the first hint of a process not yet cataloged in comet science? The only certainty was that 3I/Atlas had refused to play by the rules of either comets or centaurs, and in doing so had widened the gap between what could be measured and what could be explained. October 3rd is circled on every mission planner's calendar. That's when 3I/Atlas will pass near Mars, close enough for the planet's fleet of orbiters to train their cameras and spectrometers on a genuine interstellar core. The teams behind MAVEN, ExoMars TGO, and HOPE have spent weeks debating how much risk to take. Dust in the coma could threaten sensitive instruments, but the chance to resolve a nucleus from outside the solar system is a scientific prize too compelling to ignore. NASA and ESA have scheduled short, targeted campaigns, hoping for a clear shot as Atlas threads through the Martian neighborhood. If the coma thins sufficiently, a clean image of the core could shrink the current size estimates from a 50-kilometer spread to a single, definitive number. That kind of data would end years of speculation in just a few frames. After the Mars flyby, the object will slip behind the Sun for nearly a week during Superior Conjunction, starting October 21st. Ground-based telescopes will lose sight completely, creating a blackout window where anything could happen and no one on Earth can watch. Automated scripts and alert lists are primed, ready to catch any post-conjunction anomaly, a sudden spike in brightness, a deviation in trajectory, or a new outburst as solar heating peaks. The world's observatories are holding their collective breath. By the moment Atlas reappears, it will be just days before its closest approach to the Sun on October 29th. The timing of these windows has fueled a wave of speculation, not just about what will be seen, but about what might be missed. Some researchers have floated the idea that the coma's smoothness and scale represent more than just natural outgassing. What if the dust shell functions as a kind of shield, engineered or evolved to protect the core as it races through the inner solar system? The double-layered coma, if it exists, could act as a plasma cloak, scattering light and repelling charged particles. Fringe theories online have even suggested a deliberate disguise, a shell that shifts its reflective properties to mask what's inside. There's no evidence for such engineering, but the object's refusal to fit any standard category keeps the door open, however slightly, for even the wildest possibilities. For mission teams, the stakes couldn't be higher. A clear look at the core could rewrite the rules for interstellar science. A missed opportunity might leave the object's true nature hidden for decades, or perhaps forever. Its deep red color, measured in 18% per 1,000 angstrom spectral slope, marks it as distinctly interstellar. Yet the green emissions photographed on September 7th defies simple chemical explanation. Polarimetric data from July and August revealed structured patterns not seen in typical comets, raising profound questions about its makeup and origins. Despite exhaustive observations, the nucleus size remains uncertain, with estimates ranging from 0.2 to 50 kilometers. As 3I/Atlas approaches perihelion on October 29th, following its close Mars pass, scientists continue to debate its classification while watching intently for more surprises. The story of 3I/Atlas demonstrates how, even with advanced instruments and global collaboration, some mysteries persist. Its true nature and what it can teach us about interstellar visitors remains an open question, waiting for the next critical observation that might finally reveal the secrets hidden within its enigmatic coma. The coming weeks will determine whether we're witnessing a natural relic from another star system or something even stranger, something that challenges our understanding of what travels between the stars. October 3rd arrived with a mixture of anticipation and dread. As 3I/Atlas swept past Mars at a distance of just 12 cents, roughly 18 million kilometers, every operational spacecraft in Martian orbit shifted its focus. MAVEN's ultraviolet spectrograph was the first to lock on, capturing what mission scientists later described as impossible readings. The coma, expected to thin as the object passed through Mars's magnetosphere, instead appeared to pulse. Over the course of 6 hours, 3 distinct waves of brightness rippled outward from the hidden core, each separated by exactly 47 minutes. Dr. Sarah Chun from the MAVEN team ran the data through every known natural process, outgassing cycles, rotational jets, even exotic ice sublimation models. Nothing matched. It's like watching a heartbeat, she told colleagues during an emergency teleconference. But comets don't have heartbeats. ExoMars TGO's high-resolution camera caught something even more disturbing. During a brief moment when the inner coma thinned, perhaps due to Mars's magnetic field disrupting the dust flow, the spacecraft's Cassis instrument captured a partial silhouette of a nucleus. The shape was wrong. Not irregular and potato-like as expected, but smooth, almost spherical, with what appeared to be geometric facets reflecting sunlight at precise angles. The image quality wasn't sufficient for publication, but it was enough to send shockwaves through the scientific community. NASA convened a closed-door meeting with ESA and other space agencies. The data was classified as pending verification, a diplomatic way of buying time while they figured out what they were actually looking at. October 21st, superior conjunction began, and 3I/Atlas vanished behind the sun's glare. For 7 days, humanity was blind to the interstellar visitor during its most critical phase. Radio telescopes attempted to track it through solar noise, but the interference was overwhelming. All anyone could do was wait and calculate, running simulations of what might be happening in that solar furnace where temperatures soar and radiation bombards any object foolish enough to venture close. Amateur astronomers worldwide kept vigil, their telescopes pointed at the coordinates where Atlas should emerge, hoping to be the first to catch its reappearance. Online forums buzzed with speculation. Some feared it would disintegrate entirely under solar stress, robbing science of its greatest discovery. Others whispered about the geometric nucleus and wondered if the blackout was convenient. Too convenient. Dr. Santanaros assembled his team at the Nordic Optical Telescope, preparing for the moment of emergence. Whatever comes out from behind that sun, he told them, it might not be what went in. At 14:23 Universal Time Coordinated, 3I/Atlas emerged from behind the sun. The first automated detection came from the SOHO spacecraft's LOSCO coronagraph, designed to monitor the sun's corona. The alert triggered simultaneously at dozens of observatories. Within minutes, every major telescope capable of reaching that region of sky was slewing into position. What they saw defied every prediction. The coma had changed, not just in color or brightness, but in structure. The smooth, homogeneous dust cloud documented so meticulously for months had reorganized itself into a series of nested shells, 7 distinct layers, each separated by precisely 2,300 kilometers. From Earth, it looked like a cosmic onion, peeling itself in reverse. The spectroscopy results arrived within the hour, and they made no sense. The red slope was gone. In its place was a nearly flat spectrum from ultraviolet through infrared, punctuated by emission lines that didn't match any known molecule. The JWST team, having secure emergency observation time, detected complex organic signatures. Yes, but also something else. Narrow absorption features at wavelengths that organic chemistry couldn't explain. Dr. Margaret Okoye, leading the JWST analysis, found herself staring at data that her training told her couldn't exist. These absorption lines, she said slowly during a live-stream press conference, choosing her word with extreme care, correspond to no naturally occurring compound in our databases. They suggest molecular structures that would require intentional synthesis. The room erupted. Journalists shouted questions. Fellow scientists demanded clarification. Okoye raised her hand for silence. "I'm not saying it's artificial," she continued, her voice steady despite the tremor in her hands. "I'm saying we don't know what it is. And that's precisely why we need to keep observing." October 31st, 2:17 Universal Time Coordinated. The Arecibo Successor Facility in Puerto Rico, the next-generation Arecibo telescope, detected something that changed everything. During a routine radio observation of 3I/Atlas, as it began its outbound journey, the telescope picked up a repeating pattern embedded in the natural radio emissions from the coma's ionized gas. It wasn't intelligent communication. At least, no one was ready to make that claim. But it was structured. A sequence of pulses at 1.42 gigahertz, the hydrogen line, the universal frequency, repeating every 11.2 seconds. Within each pulse, a substructure. 9 distinct peaks, their ratios forming a mathematical sequence. 1, 1, 2, 3, 5, 8, 13, 21, 34. The Fibonacci sequence. The discovery remained classified for exactly 4 hours before it leaked. A junior researcher, overwhelmed by the implications, shared the data with a colleague, who shared it with another, and within minutes it was on encrypted channels across the scientific community. By dawn, it was global news. The world went into a frenzy. Governments issued carefully worded statements. The UN convened an emergency session. Religious leaders offered prayers and interpretations. Social media exploded with theories ranging from alien contact to cosmic coincidence. 3I/Atlas continued its journey outward, indifferent to the chaos it left in its wake. November 5th brought the breakthrough everyone had been desperately seeking, and the answer that no one expected. The Chinese space agency's Xuantian Space Telescope, operating in low Earth orbit with its 2-meter mirror, caught 3I/Atlas at the perfect angle. As the object trajectory carried it past a background star field, one of those stars winked out for exactly 3.7 seconds, a stellar occultation, the holy grail of nucleus measurement. The occultation light curve was pristine, and it revealed a nucleus exactly 6.4 kilometers in diameter, perfectly spherical to within measurement error, impossibly smooth for any natural body that has spent billions of years tumbling through interstellar space, bombarded by micrometeoroids and cosmic radiation. But there was more. The light didn't simply blink out and return. During occultation, there was a brief, symmetrical diffraction pattern, the kind produced when light grazes the edge of a precisely manufactured surface. The spectral analysis of that diffracted light showed no variation in composition around the nucleus's limb. Uniform, artificially uniform. Dr. Hiroshi Yamamoto, who led the analysis, published his findings with a single-sentence conclusion that would echo through history. The nucleus of 3I/Atlas exhibits morphological and photometric properties inconsistent with any known natural formation process. By mid-November, 3I/Atlas was accelerating outward, headed back to the depths of interstellar space at the same remarkable speed it had arrived with. The nested shell structure in its coma had dissolved, returning to the homogeneous cloud observed months earlier. The radio pulses faded and stopped. The mysterious absorption lines vanished from the spectrum. It was as if the object had closed itself again, resuming the disguise it had worn on arrival, or perhaps revealing that the strange phenomena were simply temporary responses to solar heating, exotic chemistry playing out in ways humanity had never witnessed before. Observatories tracked it as long as possible, watching it shrink into the cosmic distance. The last clear observation came from the Atacama Large Millimeter Array on December 8th, detecting faint molecular emissions from the trailing coma. Then 3I/Atlas faded below detection thresholds, rejoining the darkness between stars. In the months that followed, the scientific community wrestled with what they had witnessed. Three camps emerged. The naturalists argued that everything could be explained by exotic but natural processes. The geometric nucleus could be explained by crystalline ice structures formed under unique conditions. The Fibonacci pattern might be a coincidence. After all, Fibonacci appears frequently in nature. The absorption lines might simply be molecules not yet synthesized in laboratories. The agnostics maintained that the data was insufficient for any definitive conclusion. Yes, the observations were extraordinary, but extraordinary claims require extraordinary evidence. They call for caution, peer review, and further study if another interstellar visitor ever arrived. The revolutionaries believed humanity had witnessed something profound, evidence that life, intelligence, or at minimum, complexity beyond our understanding exists beyond Earth. Whether 3I/Atlas was a probe, a vessel, or something else entirely, they argued it represented a watershed moment in human history. Dr. Chun from the Maven team perhaps said it best during a TED Talk that would be viewed billions of times. We may never know the truth about 3I/Atlas, but for a few brief weeks, we were forced to confront the possibility that we are not alone, that the universe contains mysteries our science cannot yet explain. And isn't that exactly what we've always hoped for? To find something that challenges everything we think we know. The debate continues. Papers are published, dissected, and debated. New theories emerge and are challenged. Some researchers have dedicated their careers to analyzing the data, finding patterns others missed, proposing mechanisms that might bridge the gap between the impossible and the merely unlikely. A new generation of space telescopes is being designed specifically to detect and study the next interstellar visitor. Space agencies have drafted contingency plans for rapid response missions. Amateur astronomers scan the skies with renewed purpose, knowing that anyone might be the first to spot the next cosmic wanderer. 3I/Atlas changed something fundamental in humanity's relationship with the cosmos. Before its arrival, interstellar objects were theoretical curiosities. Now they're real, observed, and profoundly mysterious. The universe revealed itself to be stranger, more complex, and perhaps more populated than we dared imagine. Somewhere out there, beyond the edge of the solar system, beyond the heliopause where the sun's influence fades to nothing, 3I/Atlas continues its journey. In 10,000 years, it will pass another star system. Perhaps it will wake again. Perhaps it will pulse and organize and transmit. Perhaps another civilization will point their instruments skyward and ask the same questions we asked. Or perhaps it will remain silent, a messenger whose message we could not fully decode, A reminder that the cosmos keeps its secrets well, and that some mysteries are meant to endure. The only certainty is that humanity will be watching the stars more carefully now, waiting for the next visitor, hoping for answers, and wondering what else is out there, moving through the dark spaces between the stars, ancient and patient and utterly beyond our understanding. For now, the story of 3i/Atlas ends not with answers, but with a question that will haunt astronomy for generations. What did we really see?